All right, so we're starting the new unit, reviewing sequences and then looking at limits of infinite sequences. So a sequence, remember, is defined explicitly if the general term u sub n is defined in terms of n. Okay, back in math, when did we do this? Math 20, we sometimes use Tn. IB does tend to use u's. So we're kind of going to mix it around a little bit. So in this, these are explicitly defined because you don't need to know the previous term. If you do need to know the previous term, then that's called recursive definition. Now we'll look at that in a second. So the first one, u sub n, so basically first three terms. So when n equals 1, so if I start writing this out, so when n equals 1, that's negative 1 over 1. Next one, when n equals 2, that's positive 1 over 2. When n equals 3, that's negative 1 over 3. Next one, when n equals 1, that would be 2 times 3 to the negative 1, which is 2 over 3. N equals 2, that would be 2 times 3 to the negative 2, which would be 2 over 9. And then 2 over 27, keeps on going. N equals 1, that's going to be 2 over 1, which is 2. And 2 squared over 2 factorial, which will be 2. Then 2 cubed over 3 factorial, so 2 cubed is 8. Over 6 is 4 over 3. Okay, so those are some sequences. They are not arithmetic. Well, I shouldn't say that. They're not arithmetic. Geometric, this one, this middle one would be, you keep multiplying by 1/3. Okay, but the other ones are not either of those, but they're still sequences. Okay, so the next is a recursive definition. That's where you have to know the previous term or the previous two terms, or 3 or 4, but usually it's 1 or 2 previous terms. Write the first 6 terms of each of the following. So in a proper recursive definition, you got to know where you start, right? So sometimes back in Math 20 when you did this, we would ask you to come up with a recursive definition. And if you forgot the first term, really you don't have a proper definition or formula for the sequence. You have to know what you're starting with. So T1 is already given, or U1 in this case is already given to you. Second term is already given to you. Now we can get the third term. So n is 3. That means this would be 2 and this would be 1. So the second term plus the first term. So 1 plus 1 is 2. Then going from there, the previous two terms, 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. And we've got our 6 terms. Okay, so that's the Fibonacci sequence. You might recognize that one. Next one, so we're starting with 10 for our first term. So the second term, this will be 12 minus the first term. So 12 minus 10 is 2. Then 12 minus 2 is 10. Then 12 minus 10 is 2. 12 minus 2 is 10. And then it keeps alternating back and forth like that. Next one, now we're squaring the previous term. So the first term is 2. The second term is the first term squared. So 2 squared is 4. And 4 squared is 16. 16 squared is 256. 256 squared is 65,536. And then that squared is a big number. You can pause this, use your calculator, figure out what it is. Okay. So 4,294,967,000,000. Oh, no, sorry, that's billion. 4,294,967,296. Okay, so what's kind of interesting is you can graph some sequences on your calculator. Not that you're really going to be asked to do this much, but it is nice to understand how your calculator works a little bit more. So get out your calculator. Two ways to do a sequence. Well, there's probably more than this. You could use a list and put in the formula that way. But to do a sequence, you go to your mode key. If you look down to the line that has function, that's our normal calculation. We're going to choose parametric mode and then graph with dots. So it says thick, dot thick, thin, dot thin. I'm going to do a dot thick so I can see them. You might not have the choice of thick dots, just do regular dots. Okay, so now when you change that mode, when you go to your y equals, it's going to look different. Okay, it's going to be x1t, y1t. So basically x1t, that is your, t is really representing the term number. It's like your n. So just press your xt theta n key, your variable key, and it shows up as t. And then in y, you put your general term. So we're going to do this for this one, which is the third in the question one, the third sequence. So we already know what terms we should get, at least the first three. So this, if you have the fraction capability, use it. If not, you just use divide. 2 to the exponent, and then use that variable key, it shows up as a t. Okay, and then variable key factorial. Okay, so now you've entered a sequence basically. We need to then go to our window so that we'll make sure we can see it. So go to your window, okay, and take a look at the values. Those are values that sort of stayed in there from something else that I've already done. For this particular sequence, we need to think about our t, which is n. So our first term that we're starting with is 1. And let's go up, let's do 7 terms. Okay? And then we'll go up by 1. Right? Then x really is going to be your screen for those t's. So t's and x's kind of go together. So I'm going to start at 0, just so it has the y-axis, or the y-axis, which is the term value axis. And so let's go again to 7. Again, up by 1s. And then y values, those are for your term values. So we kind of already know that the first 2 terms are 2's, and then it looks like it's getting smaller from there. So let's start at 0 and go up to 3. And have a y scale of 1, just to see what we get. Okay, so now if we graph that, now you can see the blue dots are your term values. So if you trace on that, you can see it shows you, so term 1 has a y value, so a term value of 2, cursor to the right. Term 2 has a y value of 2. Term 3 has a y value of 4/3, then 2/3, then 4/15, 4/45, 8 3/15. So it actually gives it in fraction form. I'm not sure if older versions automatically give it in fraction form, but then you can find the terms. Now, you can just substitute values in, but it's just a nice way to see what the graph looks like there. Okay? So another way of doing this is if we go back to mode and go to sequence, and then again keep it dot thick, then go to y equals, and it looks kind of weird. That the little letter in front of min is actually an n. We're trying to do kind of a written n. So n, it means your term number, so it's starting at 1. Okay, it makes sense, because this is automatically for sequences. And then un is your general term. Okay, so alpha y equals, and we're p, and then 2 to the exponent variable key automatically puts an n in, and then variable key math probability, okay, factorial, and then un min is first term of the sequence. So this, put in a 2, right? You do have to know the first term of the sequence. Then, for your window settings, again, it looks a little bit different. Now it's going from n min of 1, n max, we're doing 7 terms, that's what we did before. You can keep it as 10, but we'll do 7. Plot starts at 1, steps up by 1, okay, so that's where the X is your screen, so again, keep it 0 to 7, up by 1s, and then your Y, so it's copied this out from our last calculation, so Y are your term values, 0 to 3, up by 1s. Now if you press graph, it looks the same, right? And it gets, you press trace, now it's your N equals 1, Y equals 2. So the variables are a little bit more relatable to what we've been doing so far. We usually use N for term numbers. Okay, so it says 5 terms of the sequence to record here on both of these. So 2, 2, 4/3. We already had that from question 1. Then 2/3, then 4/15. Okay. All right. So now let's look at the limit of a sequence. So it says let L be a real number. The sequence with those curly brackets UN, so that represents a sequence with those curly brackets, has a limit L as n approaches infinity. If given any positive number epsilon, so that's a Greek letter epsilon, there is a positive number m, capital M, such that for all n greater than m, so basically term numbers bigger than m, that difference between the term value and the limit is less than epsilon, okay? So you're going to do in university a lot of what you call epsilon delta proofs. Epsilon is a small number, right? So we want this basically is approaching, so the term here, that term value as n goes to infinity, minus the limit is getting really small, okay? Then we know it converges. It's got to be small. Otherwise, if it's getting bigger, it's not going to converge, it diverges. So we write the limit of u sub n as n goes to infinity equals L, and say that the sequence converges to L. So if the limit does not exist, then it diverges. So we're going to look at some graphs here to help us with this. I'm just going to minimize. Okay. So this is describing the definition above. So this sequence defined here is plotted up to, I guess, n equals 10. Okay, and so then there's some other lines. Basically, because of that, the -1 being in the brackets within, so they're alternating, going back and forth, but they're getting closer and closer together. Okay, and so in this case, really, when your n value is greater than some m, what that says, so basically bigger than about 5, then these are approaching the limit, so halfway in between there. So that kind of means here, this is like your, a little bit hard to draw, limit value here. This value from the green to that is epsilon, and this value here is epsilon. Okay, so that the absolute value of the difference between the term value and the limit is less than epsilon. Okay, you can see they're between those red and green lines. as n goes to infinity. Then this one down here for this definition, so it's not really alternating, they're getting closer and closer. And so in this case, it's almost the same expression. The green and red are the same. So now it's approaching a limit. Halfway in there. And then this is your epsilon. This is epsilon down here too, but there are no term values there. So in this case, basically n is greater than about 5 as well. Okay? So they're approaching a limit. So algebraically determine the limit here. So these are the graphs that are above, but we're going to do it algebraically. So let's do the first one. So this, if I split this up into two terms, I get 3 plus 1 to the n over n. Okay. And so as n goes to infinity, 3 stays. And then 1 to the n is to positive 1, right? So it stays as 1. And over, that basically becomes infinity. So that approaches 0. So it's going to be equal to 3. Okay, which is what it looks like in our graphs. And then limit n approaches infinity. So that then would be 3 plus negative 1 to the n over n. Okay, so now we have to think about what happens. So when n is an even number, so this is going to be 3 plus, it's going to be, when n is even, it's going to be 1 over n when n is even. Okay, so therefore equals to 3. We already did that one on the left. And then when n is odd, it's going to be negative. And so that's also equal to 3. Okay, you might think, well, why bother? But there are times where you have to consider both cases. So that's what we're doing here. So therefore, limit n goes to infinity. Okay, both of them are 3. Different graphs when you graph them, right? But they both have a limit of 3. Great, so then let's take a look at the squeeze theorem. Not sure that you've talked much about this before. You may have read about it, but they let three sequences defined by u, v, and w be infinite sequences. Limit be the same for u and w. And if there's an integer, capital N, for which the sequences are basically from smallest to largest for all n, lowercase n, greater than capital N, then v will have the same limit. So it basically sandwiches this. So if this has a limit of L and this has a limit of L, the inside of the sandwich has a little limit of L. Okay, so that's why it's sometimes called the sandwich theorem. In this case, we call it the squeeze theorem. You're squeezing into V there. So you'll hear it both ways. So show that this sequence, so curly brackets tells you it's a sequence, converges, and find its limit. Okay, so we need to think about, in this case, sequences, well, actually, expressions that represent a sequence. So expressions that we know cos n over n is between. Okay, so if you have a trig, primary trig ratio like cos or sine, you know that cos, the maximum value for cos is 1 and the minimum value for cos is -1. So you know this. So that's helpful. Now our expression is over n, so we can divide by n. Okay? And we can include the equal signs. So now really we want to take the limit of the leftmost one. Okay, well, limit of the leftmost one is going to be 0. Okay, and then the limit, so we can take the limit of all of these if you want to show it all at once. Okay, so the limit as n goes to infinity is 0. N to, where n goes to infinity is 0. So that must mean the limit as n goes to infinity of cos n over n equals 0. Okay. So that's a kind of a neat way of coming up with some limits that you may not have done before. Okay. Absolute value theorem. So this is when you have negatives in the base in some of your sequences. So let U be an infinite sequence. If the limit of the absolute value of that sequence as n goes to infinity is 0, then the original is 0. So it says use the absolute value theorem to determine this limit. So we basically want to take limit as n goes to infinity of absolute value. Okay. Really, we didn't need the sequence expression here, because as n goes to infinity, that's assuming those terms are going. In any case, now we're going to take the absolute value. So that means that really is going to be limit as n goes to infinity. So depending on what, if n is, well, if n is odd, then the exponent would be even. This would be a positive. So it would give you a positive. If n is even, the exponent would be odd. It would give you a negative. Then you take the absolute value. So when we can really just show it as 1/2 to the n minus 1. So that's what you're taking the limit of. Okay, and then to show this, because you know that that exponent is increasing, you know the 2 is going to have a higher exponent. If you can simplify these, then do so. All right, so that would be 2 over 2 to the n minus 1. So don't just skip steps or skip work, like you're showing how you know things are true. So this is going to be 1 over 2 to the n minus 2. Okay, so now the denominator is 1, the numerator is 1, the denominator is basically approaching infinity minus 2, which is going to be 1 over infinity, which is 0. Okay, so the limit is going to be 0. Okay, that's the end of that lesson.